I think you can start now, Tracy.
Good morning, everyone. Welcome to this session of the IMS Lawrence Brown PhD Student Award. So this award is in honor to honor Dr. Lawrence Brown, and was established using the fund from his family and friends. And Dr. Brown is a former professor of statistics at the Wharton School, University of Pennsylvania. He not only has groundbreaking contributions to statistics, he's also well known to be a great mentor to graduate students. And the selection of this award is this is a very selective and prestigious award. And today we will have presentations from the 3 recipients this year. So the first speaker is Yichen Zhang from Purdue University. And Yichen, would you like to start your presentation?
Sure. I'll share the screen now. Thank you very much for the introduction.
Oh, sorry, I forgot to mention. So if you have questions, you can either type in the Zoom chat box, or you can raise your hand. Use the raising hand button on Zoom. Yeah, Yichen, please go ahead and start.
Yeah, can you see my screen now?
Yes.
Yeah, great. Okay, so good morning, everyone. Today I'm going to talk about first-order Newton type estimator for distributed estimation and inference. I'm Ichan Zhang. It's my greatest honor to receive this award and to present here at this invited session. I'm currently an assistant professor at Kraner School of Management at Purdue University. The presented work is joint with my PhD advisor, Xi Chen, and also Professor Wei Dongliu from Shanghai Jiaotong University. The work is done during my PhD at Stern School of Business, New York University. Again, as I said, it was really my great pleasure and honor to present here. Without further delay, let's start the presentation now. So let's start from a general estimation inference problem for a population parameter CR star. Here CR star is the minimizer of population risk function, capitalized F theta, which is an expectation of the convex loss function F theta psi, which can be non-smooth when psi is a random sample followed from a distribution pi. So the random sample could be typically could be a set of independent variables and dependent variable y, a set of independent variable x and an independent variable and a dependent variable y using a regression setting. So for example, when we are in a linear regression, we would use the squared error for the linear for the loss function, or we in logistic regression we have the logistic function for the loss function, and for quantile regression linear support vector machine, here is the individual loss function, and we can see that because of the indicator function here, and also because of this this function which would have non-smoothness in non-smoothness. So the loss function could be non-smooth in this framework, and we would just denote G theta psi to be a subgradient of F in the non-smooth settings. So let's start from the estimation. From a typical estimator would be the empirical risk minimizer, that we replace the population risk F here by an empirical risk function, which is we can say a sample average of the loss functions over the and RID samples. So with this estimator, we can build asymptotic normality for the estimator theta hat. And for example, for fixed dimension P, we would, so the dimensionality we use P here in this talk. For fixed dimension P, we will say that theta hat is having this normal distribution in a, so the variance is in a sandwich form, and the variance is in a sandwich form with A here to be the covariance matrix of the subgradient, and sigma here is the population Hessian matrix. And also when P goes to infinity, we would have to write it in this way. We have to project that onto a fixed dimension fixed dimension vector, or in this case, we just project that into onto a unit length vector W. We can also extend to several vectors, but it needs to be a fixed dimension. So the inference, the asymptotic normality will be written like that. In both of the settings, we are interested to make an estimator, to make an estimator of W transpose sigma inverse A sigma inverse W in order to conduct inference. So here we just have the asymptotic normality. We need an estimator for that to do the inference. Okay, so that's for the background. Thanks to the development of the big data, we would be now having dealing with data sets with both large N and P. So we are in this talk, we are interested in distributed estimation and inference for theta star when the sample size and the dimension are both large. So a typical distributed system, or we see distributed environments, will be looking like this. So we have a master machine, and we have data located on the local machines. We say worker machine 1 to worker machine L. So the master machine is trying to collect the data from, either collect the data or collect some we say statistics from the local data. And make some updates to some term we cared, and we update that from the data on the local machine. So in applications that could be like a wireless sensor network, there's a lot of wireless sensor nodes everywhere in place, and we just collect the data from the sensor nodes and make computations in a master machine, or maybe on the cloud server or whatever. So that's in distributed environments. I also like to mention that distributed algorithms would also be useful not only on the distributed settings where the data are separated. It is also useful. Distributed algorithm is also useful when we have centralized data. But sometimes the data could be too large to fit into the memory. Like as we know that the data is stored on a hard disk, which could be hundreds of gigabytes, or even terabytes, or even petabytes. But the main memory of our computer is basically tens of gigabytes. So if the data is too large to fit into the memories, and most of our existing statistical method, which relies on the optimization tools to get the estimators, would not working because we are not able to compute those. So we may rely on some distributed algorithms to do so, even if we have a data centralized on a hard disk, but not able to get into to be put into memory. Or other settings like real-time streaming data that may be online online data that arrives at the processor at a very high speed, that we cannot store all the data, and we'll only be able to see one data once. Okay, so in this case, we can also consider that as a distributed system, but the worker machines will become active sequentially. So first time we like swap the first piece of data into the main memory, it's kind of like activate worker machine 1 and then go ahead to the second piece of the data, which we would say the second worker machine. So in this environment, in the distributed environment, we are interested to design a distributed algorithm like we call theta hat distributed, which we want that to approximate the empirical risk minimizer that evaluate on the pooled or on the full data set, entire data sets. We want that to be having low communication cost and low computation cost. We don't want to exchange too much data between the master machine and worker machine. At the same time, we want to we want to achieve a very high accuracy for the distributed estimator, which that we want that the distributed estimator to be very close to the ERM on the full data set, entire data sets. Beyond that, we are also interested in making inference. So we need to estimate the W transpose sigma inverse A, sigma inverse W in a distributed environment. It is easy to see that the A here can be estimated by its sample version. A here, recall that A is the covariance matrix of the gradient function evaluated at the true theta star. We can replace that by a sample version, sample covariance estimator at the final estimator theta hat. Second thing is that we need to construct an estimator of sigma inverse W or sigma, but as we discussed in the first page of the talk today, we are also considering some non-smooth loss functions which we may not have empirical hashing. For example, in quantum regression support vector machines, they both have population hashing matrix, actually linear support vector machine. They both have population hashing matrix, but they don't have empirical hashing matrix. So it will be challenging to consider to estimate sigma or sigma hat or sigma or directly sigma inverse W when we receive the data. And also we want this procedure to be fitting into a distributed environment. Okay, so how to construct an estimator of the sigma, of sigma or sigma, it's not of sigma or sigma inverse W. Let me finish this page first. We want that to be computationally efficient, that we only use the first order information, and we want that to be easily scaled up to a distributed setting as data stored on different machines. And finally, we want to deal with non-smooth loss function F and divergent dimension. I received a question in the chat about whether we could use resampling techniques. Definitely, we could consider to use resampling techniques. However, it's also interesting. It's challenging and also interesting to see how to do resampling techniques in a distributed environment, because you don't want to resample over the machines to using other data from the other machines. How to carefully design estimators and how to make sure your resampling techniques will lead to good results is also an interesting question, an interesting problem. But it's not our focus at this talk today, but again, it's interesting problem and interesting work. So let's just try to talk about some notations in this talk. We use dk to be the data on the worker machines, k equals to 1 to L. So we have in total L machines, L local machines, and we have local sample size M on each local machine. And the total sample size, the entire sample, we use sample size N, which is L times M. Again, M is the local sample size and L is the number of machines. And we allow not necessarily even distributed machines. So we can replace the N equals to L by L times M by M1 plus M2 plus going ahead to end up ML equals to N. Okay, so a very straightforward and popular method is we call the average divide and conquer. It's a one-shot method. So typically you calculate a local empirical risk minimizer, only use the local data on each worker machine, on each local machine. And then you aggregate those local empirical risk estimators by making an average. We write that to be a DC estimator. It is short, in short of to be a short version of divide and conquer. This is a very popular method for the distributed estimation. There's numerous literature on using this method in a lot of different statistical problems like ridge regression, kernel ridge regression, non-parametric methods, cubic M estimators, and quantile regression. I just listed, and also some high dimension problems. I just listed a few here. There are plenty more that have contributed to this area that I haven't mentioned in this page. I just want to say that for this type of method, it's very straightforward and very popular and very easy to compute. The only issue is that, so typically the inference would fail when N is greater than some constant times M squared. So it means that when the number of machines is larger than the local sample size, so when L is larger than the local sample size M, then this estimator could generate a good estimator, but it's not as good it's not good enough to allow we use the same inference procedure as the empirical risk minimizer on the pooled data set. It's typically because the bias of the divide and conquer estimator cannot be reduced by the averaging. We'll go into an example, but if you look into some of these literature, you would mostly see that they will either require in condition that saying the number of machines must be L equals to O of M, or some literature just compare the results when L exceeds that, and you will see a sharp drop on the performance of the statistical inference. So let's, using this idea, let's start with a very typical method called divide and conquer SGD. That typically means that on each local machine we solve the local empirical risk minimizer by stochastic gradient descent. We don't have much time now, so I will just skip the stochastic gradient descent, the introduction of stochastic gradient descent here, and we just would not have to. We just need to know that it is a very efficient solver for the empirical risk minimizer. Efficient in terms of computationally efficient, not statistically efficient. It just means computationally it is very fast. It has a computation complexity of O and P. M is the number of iterations, which is also the which is also the local sample size, and P here is the dimension. We can also use a mini-batch SGD. It has the same computation complexity as long as we just view one data at view once of each data point. Here is some examples. We talk about linear regression, logistic regression, quantile regression, linear support vector machine. So although the quantile regression linear support vector machine is not derivative, we can use its subgradient descent. We can use its subgradient to define the G, and it's still well defined here. And I also listed some regularity conditions that we need to build for our theorem. So let's get into our first result, is the theoretical result for the Dc Sgd. So under some regularity conditions, we would see that the mini batch Sgd, this is the result on a local machine, would have an error rate as square root of P over N. Well, we also evaluated its bias. We can see that its bias is at the order of P over N. So with that on hand, we can build the convergence result for the distributed, for the divide and conquer Sgd, which will be having a rate of looking like that. So it's very easy to understand why it looks like that. It's because when we decompose the error, squared error, with a variance here and a bias, squared bias here, we can see that, we can see that the variance term can be reduced by averaging. However, the bias term cannot be reduced by averaging. So the P over M here is the local bias, which also carries into the bias for divide and conquer method. So we can see that this method will suffer from local bias, local sample size M when M is small, and when the local sample size is very small. And when bias dominates the rate, we cannot either conduct inference unless one can carefully quantify the average bias. So such requirement or such condition is almost necessary, and we build that in the paper, but I would not have time to talk about that here. So how to avoid the constraint? So so key ideas are the three of the following. So one is that we can try to use better local statistics to do the aggregation, and we can use a better aggregation than other than the averaging. And finally, which is most important, we need to consider multiple rounds of aggregation for the requirements. So this method, divide and conquer method, is a one-shot method, which means there are just one round of aggregation. So with a multiple round of aggregation, that builds on the idea of Newton-Raphson's method, which in statistics we have Newton's one-step estimator. So basically, we do a Newton's one-step estimator, like looking into the entire data, we do a Newton's one-step estimator. So when doing a Newton's one-step estimator, we need to evaluate a Hessian, empirical Hessian and an average version of the gradient. So they can be done in a distributed environment, and it achieves a better performance because it actually just is as good as doing a Newton's one-step estimator to solve the empirical risk minimizer. So, and also existing literature has proved that there are some asymptotic equivalence when we replace this empirical Hessian estimator by an empirical Hessian on the first machine. So this is by the paper from Michael Jordan, Jason Lee, and Yun Yang, and it is also sharing the same spirit as the Dane in 2014. So this means that we are actually creating a estimator sigma hat to approximate sigma here. It still requires the empirical Hessian exist. And also the computation inverse of the local Hessian is still time consuming when P is large. So instead of considering estimator of the empirical Hessian sigma, we can actually directly construct an estimator of sigma inverse A instead of sigma. So instead of doing things like this one, we can construct an estimator of this term as a whole. And we want to do that only use the first order subgradient information. That we don't want to get any access to the Hessian or we say second order subgradient information. And we want that only, first of all, it not only give us computation efficient, but it also avoid the issue on the non-smooth loss. So it allows the non-smooth loss case. And it also allows divergent dimension in practice because, yeah, in a divergent dimension, that's time consuming.
5 minutes left.
Sure, yeah. So a similar form appears when we conduct inference, as you could recall that we want to, when we are doing inference, when we are doing inference, we want to estimate this term, and this term can be done in, like this one, as the first part as a whole and the last part as a whole. So trying to do that like this would be very important to not only for distributed estimation, but also for distributed inference. This technique is also used in some other applications like LDA, as we only need to create estimators for sigma inverse A, not actually sigma. So we propose a method called first order Newton type estimator. I will skip the details on how to create this estimator, but the spirit of that is to create a linear recursion that could solve sigma z equals to A. Solving sigma z equals to A would generate a z equals to sigma inverse A. So we use this recursion to approach sigma inverse A. So here is some details of how to show that sigma show that the tilde would converge to sigma inverse A. So with that on hand, we can estimate sigma inverse A using a linear recursion. And it is still challenging because we actually don't have access to the sample version of sigma. So instead of using the sigma, we approximate the sigma z tilde by a gradient difference. So simply by the mean value theorem, we can replace the sigma multiplied by z by a gradient difference as long as we have a good estimator of the gradient. So here BT is a subset that creates a good enough estimator for the gradient, and we use that to approximate sigma z tilde. With that on hand, we have our first order Newton type estimator. So here is the detailed algorithms. I guess we don't want to get into that again, but just using a Newton's estimator, and when we need to create sigma, when we need to update sigma inverse A, we replace that by estimator and using the gradient difference to estimate that. So it's a low communication cost method, and I'll have to skip this part. I also want to say that it is closely related to the SVRG, as you may have heard, but technically it is can be considered as a generalization. So we can show that under some assumptions that this distributed method would be able to this method can be easily done in distributed setting because everything is a summation. So this distributed method can achieve any arbitrary close to the global empirical risk minimizer asymptotically. So here it means that for any gamma greater than 0, we can find, as long as we have one more round or several more rounds of running these algorithms, we can achieve a good enough result. But that's for the smooth loss function, and we also have the result for non-smooth loss function. But non-smooth loss function is a little more complicated.
1 minute left.
Sure. Yeah, finishing very quickly. So as we said that our method is also able to create an estimator for the sigma inverse W, so it is also suitable for the inference procedure. So I'll skip some numerical results. Basically, these numerical results are to support our methods work for our methods work in empirical experiments. So to summarize that, just 1 minute to summarize. To summarize that, we create an efficient first-order Newton type estimator for estimating sigma inverse W for any W. When we are doing an estimator, we are using W equals to the average gradient. When we are doing inference, we can use any arbitrary W that we want to project to. So the key idea is to use the classic gradient to approximate the Newton step. And this paper is just recently accepted at JASA, and you can see that from in archive. And some other work I mentioned in this work, some other results I mentioned in this work are in two of my other publications. Yeah, thank you very much. And this is all for my talk today.
Thank you for the great presentation. Yeah, so here I have a question from the panelists. Okay, so the question is, could we use resampling techniques such as bootstrap to avoid the estimation of this sigma and construct the confidence intervals?
Yeah, I mentioned that part a little bit in the talk. So we definitely can use that resampling techniques, but it's also interesting it's a very interesting question to see how resampling techniques work in distributed settings, because we don't want to use data from the other machines, and it is a very interesting questions, but it's not what our method worked on. Yeah.
Thank you. Yeah, for time constraint, maybe we will leave other questions to the end of the session. Just to let everyone know, we have a 15 minutes floor discussion after all 3 talks.
Sure.
Thank you, Yichen.
Glad to answer the questions then. Yeah, thanks. I will stop the sharing and.
Okay, so our next speaker is Ilmun Kim, and Ilmun, would you like to start?
Can you hear me?
Yes, I can.
Yeah, great. Yeah, so hello everyone, and thank you for the introduction. And I want to start by saying that it is a great honor and also pleasure for me to receive this Brown PhD Student Award and present my work at JSM today. Okay, so today I'm gonna talk about Minimax optimality of permutation test. And this talk is going to be based on joint work with my PhD advisors, Sivaraman Balakrishnan and Larry Wasserman in Carnegie Mellon University. Okay, so to motivate our study, let me begin by illustrating that there are 2 cultures in approaching hypothesis testing problems. So first of all, in statistics, we put more emphasis on type 1 error control rather than type 2 error control in general. So it is more important to precisely characterize the null distribution of a test statistics. And in general, it is difficult or even impossible to know the exact distribution of the test statistics. So we often rely on large sample theory to understand the limiting null distribution of our test statistic. In computer science, on the other hand, people are not so interested in tightly controlling the type 1 error rate, but they are more concerned with theoretical optimality of a given test, mainly in terms of sample complexity. And they typically make use of concentration inequalities to analyze their test that comes with a finite sample guarantee. However, the resulting test often depends on unknown or very large constants in their critical values, which brings up some practical issues. So in this context, the goal of the study is to combine these 2 cultures using permutation test, which has finite sample validity as well as theoretical optimality. Okay, so the use of permutation methods dates back to Fisher in 1935. And I believe that many of you are already familiar with the permutation test. So let me very briefly walk you through the procedure. So suppose we have n observations, x1 through xn, and given these samples, the permutation procedure relies on the following iterations, where in the first step, we randomly permute the class labels of the data. And then in the second step, we compute the test statistic based on the permuted data. Okay, and then we repeat this procedure multiple times, which results in a set of permuted test statistics denoted by T1 pi up to TB pi. And then we also compute the test statistic denoted by T sub n based on the unpermuted data sets. And then we compare it with the permuted test statistic and see how significant T sub n is compared to the permuted test statistics. And more formally, we count how many permuted statistics are greater than the original statistic and compute the following the permutation p-value. And we reject the null when this p-value is less than a pre-specified significance level alpha. And the resulting permutation test has many attractive properties in terms of type 1 error control, which is summarized in this slide. So first of all, the permutation test has uniform and non-asymptotic type 1 error control, which means that the type 1 error is less than or equal to alpha over the class of null distributions, and this guarantee holds for any finite sample size. In addition, the permutation test is distribution free for any type of test statistics, and it does not depend on unspecified constants in their critical value, so that we can easily implement this procedure in practical applications. However, I want to emphasize that the permutation test is not assumption free. In fact, we need to assume that the samples are exchangeable under the null, which is not a strong assumption for many problems that we are interested in, at least in this talk. Okay, so to further highlight the strengths of the permutation test, let me contrast it with an asymptotic test, which relies on a limiting distribution. So it is often satisfactory to use an asymptotic test, especially in a fixed dimensional setting, but this is no longer the case in a high dimensional setting where the distribution can change arbitrarily with the sample size, as well as other underlying parameters. So let me briefly demonstrate this difficulty in the next slide. Okay, so suppose we want to test whether two multinomial distributions, say P and Q, are the same or different. And one natural test statistic for this problem is a U statistic, which is an unbiased estimator for the squared L2 distance between P and Q. And here, the detail on this test statistic is not so important, but the main message that we can get from this test statistic should be clear. So here are three histograms of the null distribution of the test statistics by changing the number of bins denoted by D from 5 to 10,000, while fixing the sample size to be 100. So from the figure on the left, we see that the distribution of this test statistic is fairly skewed, and it looks like a chi-square distribution when the number of bins is much smaller than the sample size. On the other hand, when the number of bins is comparable to the number of observations, as you can see, that the distribution becomes more symmetric, and it now looks more like a Gaussian distribution. And even more dramatic shape can be observed when the number of bins is much larger than the sample size, as in the last figure. And in this case, the distribution of the test statistic becomes much sparser, and it behaves like a Poisson distribution up to some scaling factor. So these empirical results clearly highlight the difficulty of estimating the limiting the distribution of a test statistic. And from this, it is also clear that constructing a reliable asymptotic test is difficult or even impossible in high-dimensional settings where, basically without any further assumption, this is very challenging test. So in contrast, I want to re-emphasize that the permutation test does not require any knowledge of the limiting distribution, and more importantly, it is valid in any finite sample size and for any type of tested statistic under the minimum assumption. Okay, so far I have illustrated that the permutation test has good properties in terms of type one error control, but now let me describe some challenges associated with the permutation test. So the first challenge is about power. So since the observations under the permutation sampling are no longer IID, it is difficult to study the power of the permutation test. So the previous studies on these topics are mostly concerned with asymptotic results, focusing on a simple linear type test statistic. And so we don't yet have a clear picture of when the permutation test is going to have high power. The second obstacle of the use of the permutation test is computational cost. So in order to compute the permutation p-value, we need to recompute the test statistics multiple times, and it can be very expensive depending on type of test statistics. So in order to overcome this difficulty, there have been some alternative approaches relying on concentration inequalities, sample splitting, and so on, but this is not the main concern of today's talk. And the last challenge that I want to mention is the exchangeability assumption. And as I said before, the universal validity of the permutation test heavily relies on the assumption that the data are exchangeable, at least under the null. However, in some cases, we cannot make such an assumption. And so studying the robustness of the permutation test to known exchangeability has been an active research topic. Okay, so I believe these are all important issues, but in today's talk, I will focus on the first challenge and present some results regarding the power aspects of the permutation test. Okay, so as I said before, there have been several studies on the asymptotic power of the permutation test, which can date back to Hofding in 1952. And in this line of work, people study the limiting distribution of a permuted tested statistic, building on some techniques such as combinatorial centrolim theorem, and present an asymptotic power expression of the permutation test. But they are mostly concerned with a fixed dimensional asymptotic setting and focus on a specific type of tested statistics, such as T statistic, F statistic, and empirical processes under certain assumptions. And similar strategy has been used to prove the robustness of permutation tests to exchangeability, but again, mostly focusing on a specific type of tested statistic in a fixed dimensional setting. In the last 5 years, people have started looking at non-asymptotic properties of the permutation test. And more specifically, people have studied concentration inequalities of a tested statistic under the permutation law, which in turn allow us to understand non-asymptotic power of the permutation test. And I just listed a few papers that cover non-asymptotic aspects of the permutation test. And I want to emphasize that the most similar work to the paper that I'm presenting today is Barrett et al., which has been accepted to Annals of Statistics. And similar to our work, they present Minimax optimality of the permutation test based on U statistics for independence testing, as well as other interesting results, including certain hardness result of independence testing. Okay, so having discussed limitations and related work, let me introduce our proposal called two moments method, which is a generic technical recipe for analyzing the non-asymptotic power of a permutation test based on the first two moments of a test statistic. So before jumping into technical details, let me provide a pictorial intuition for the proposed method. So at a high level, the power of the permutation test is determined by a distance between the permutation distribution and the alternative distribution of a given test statistic. So here the permutation distribution can be understood as the histogram of the permuted test statistics, which is a random distribution depending on the data. And this distance between these two distributions can be roughly characterized by the first two moments of the test statistics as in the figure. And more specifically, if the signal, which is defined as the difference in means, is significantly larger than the noise, which is the maximum of the variances, then we can expect that the permutation test has high power. On the other hand, when the signal is much smaller than the noise, then there is no hope that we can reject the null, which leads to low power. So in other words, if we have a good understanding of the first two moments of the test statistics, then we can roughly characterize the power of the permutation test as well. Okay, so having this intuition in mind, let me provide the main result of our work. So first of all, we assume that the expectation under the permutation law is equal to 0. And this assumption is satisfied for use statistics that we will study later on. And a more general statement without this assumption on the expectation can be found in our paper. We then assume the number of random permutation is greater than 1 over alpha squared times log of 1 over beta up to some constant. And importantly, the lower bound of B is independent of the sample size, but only depends on the desired type 1 error rate as well as type 2 error rate denoted by alpha and beta respectively. And then lastly, we assume that for each distribution in the class of alternatives, the expected value of the test statistic, which is basically the signal, is greater than the square root of the variance of the test statistic plus square root of the expected variance of the permuted test statistic. So in other words, we assume that the signal is greater than the sum of two noises from the original distribution as well as the permutation distribution up to some constant factor. We then have the following guarantee that the uniform power of the permutation test over the class of alternatives is greater than 1 minus beta. So to put it another way, we can characterize the conditions under which the permutation test is uniformly powerful based on the first two moments of the test statistic. So therefore, the problem boils down to understanding the mean and the variance of the test statistic. I think there is a question, but is it okay for me to answer the question at the end of the talk?
It's up to you.
Yeah, I think that's yeah. I think
it's okay.
It will be better. Yeah. Okay. So great. So if we restrict our attention to a certain statistic, namely U statistic, then we can further simplify the previous condition. So suppose that we draw IID observation x1 through xn from a distribution px, and similarly y1 through yn from another distribution p sub y. And then given a symmetric corner h of x and y, the two sample statistic is defined as follows. It looks quite complicated at first glance, but we can simply interpret this as a difference between within similarity and between similarity. And the idea is that when px and py are the same, the expectation of the statistic becomes 0. And otherwise, the expectation of the statistic is going to be greater than 0. And roughly speaking, the expectation is associated with a weighted L2 distance between px and py. And depending on the choice of corners, this statistic includes corner MMD and energy statistic, which are commonly used statistic for two sample testing. And we can similarly define a statistic for independent testing. And now suppose that we observe IID pairs of X and Y from a joint distribution P sub X and Y. Then given corners H sub X for X and H sub Y for Y, we can define the U statistic for independence testing as follows. So again, it looks quite complicated, but roughly speaking, the first term estimates the square of the joint distribution P sub X and Y, and the second term estimates the square of the product distributions Px and Py, and the last term estimates the product of the joint distribution and the product distribution. So in summary, this statistic can be viewed as an unbiased estimator for a certain weighted L2 distance between the joint distribution and the product distribution, so that expectation is 0 whenever X and Y are independent. And this type of statistics has been widely used in the literature of independence testing, and examples include corner H6 in Grattan et al. And distance covariance in CK et al. Okay, so now focusing on the U statistic for two-sample testing as well as independence testing, we can simplify the previous conditions on the two moments method. So the key lemma here is that the variance of the original tested statistic is larger than the expected variance of the permuted tested statistic up to some constant factor. And therefore, we can show that the permutation test based on a U statistic becomes powerful whenever the signal is greater than the square root of the variance of the U statistic. And this result is quite nice in the sense that we don't have to compute the variance of the permuted tested statistic, which is often difficult due to non-IID nature of permutations. In addition, the expectation and the variance of U statistics have been quite well studied in the literature, so we can easily build on the previous results to study the power of the permutation test. And another point that I want to make is that for the U statistics, we can improve the dependence on alpha in the condition from 1 over alpha to squared log of 1 over alpha. And this result can be proved using an exponential concentration bound for a permuted U statistic with some extra conditions. But in the interest of time, I might not be able to cover this result, but in case anyone is interested in this result, then they can take a look at the paper on arXiv. So, okay, so far I have presented sufficient conditions under which the permutation test becomes powerful. And a natural question is whether these sufficient conditions are indeed necessary. So I want to provide a partial answer to this question from a Minimix perspective. So to do so, we need to formally define Minimix rate optimality for testing. So suppose we want to test whether two distributions, say P and Q, are the same or different. And in general, if two distributions are too close, then no test can detect the difference with finite samples. Therefore, we consider a subset of alternatives where a certain distance between two distributions is at least greater than epsilon n. So in this setting, the Minimix power is defined as the worst case power of an optimal test over the subset of alternatives where the distance between P and Q is at least greater than epsilon n. So mathematically, the Minimix power is defined as the supremum over all level alpha tests, and then we consider the infimum power of a test over the subset of alternatives. Then our first goal is to characterize the minimum value of epsilon, known as minimum separation, for which the Minimix power becomes non-trivial, meaning that it is greater than alpha but less than 1. So pictorially, we want to find out epsilon star, for which the problem is not too difficult. and also not too easy for an optimal test, like the situation in the middle of these figures. Okay, and then in general, it is impossible to obtain the exact Minimax optimal test, especially for non-parametric problems. And so we'd rather be interested in achieving Minimax rate optimality. Here, we call a test is Minimax rate optimal if the minimum power of a given test over the class of alternatives determined by epsilon n is greater than 1 minus beta, where beta is some small constant. And if this bound holds, oh yeah, thank you. Whenever the epsilon is the same as epsilon star up to some constant factor, then we call this test is Minimax rate optimal. And this type of Minimax analysis for testing was initiated by Inkster and his collaborators. And it has received much attention in recent years. And here is a very limited collection of work that studies Minimax optimal test in the context of testing for multinomials as well as densities. However, I want to point out that the previous optimal tests often depend on unknown constants in their critical values. So it's not clear how to implement such a test. For example, Chen et al. In 2014 studied the minimum separation for multinomial two-sample testing in L1 distance, and they show that the minimum separation for this problem is proportional to the maximum between the following two quantities, which is a function of a sample size n and the number of bins denoted by d. And they further show that a modified chi-square test achieves the Minimax rate optimality for this problem. And in particular, they show that if we reject the null when a modified chi-square test statistic is greater than some constant times square root of the minimum between n and d, then the resulting test is Minimax rate optimal in L1 distance. However, in practical applications, we don't know how large this constant c should be in order to control the type 1 error rate. So it has been unknown whether there is a Minimax optimal test that can be practically implementable. And similarly, building on the work of Inkster, Arias Castro et al. In 2018 proved that the minimum separation for two-sample density testing in L2 distance is of order n to the power of minus 4s divided by 4s plus p, where s is the Holder smoothness parameter and p is the dimension of the data. And then they want to show that the proposed test in their paper, whenever their test statistic is greater than certain threshold, which depends on unknown constant, and they show that this is a Minimax rate optimal. So these results motivate us to question whether it is possible to obtain a Minimax rate optimal test that tightly control the type 1 error rate, and it does not depend on unspecified constants, so that we can use it in practice. So the answer turns out to be yes, and we show that the permutation tests are indeed Minimax rate optimal in many problems, and we can show these results using the two moments methods that I described earlier. Okay, so here is a non-technical summary of our results. For the problem of two-sample testing, we revisit several existing test statistics, such as chi-square test statistic in Chen et al. And binning-based statistic in Arias Castro et al. And show that the permutation test using the same test statistics or a slightly modified version achieve the same Minimax optimality as their theoretical test that depend on specified constant in the critical values. Moreover, we apply our technique to Gaussian MMD, which is one of the commonly used test statistics for non-parametric two-sample testing, and show that the resulting permutation test is Minimax rate optimal under certain smoothness assumptions. And similarly, for the problem of independent testing, we show that the permutation tests using a certain type of test statistics are, again, Minimax rate optimal, including flattened test statistic by Diakon Nicholas and Kane in 2016, and Gaussian H6 by Gretton et al. In 2005, for the study by Mainyawi et al. In 2019. Again, all of these results can be proved using the two moments method described earlier. And this illustrates that our sufficient conditions are tight for some two sample and independent testing problem from a Minimax perspective. Okay, so to wrap up, permutation tests have a uniform and finite sample guarantee for any tested statistic, which I think really nice properties, especially when we need to deal with high dimensional and complex data sets. In general, it is difficult to study the power of the permutation test due to the combinatorial nature of the permutation procedures. So in this work, we have provided tools for analyzing the power of the permutation test, including two moments method and exponential concentration inequalities for a permutative statistic. Using these tools, we have demonstrated that the permutation test has minimax optimal power in many problems, which gives a strong justification for the use of permutation tests in many practical applications. Okay, so that's what I want to say today, and thank you for your attention.
Thank you for the great talk. We have received 3 questions from the audience. To save time, I have typed them into the chat box, and you can choose to answer all or some of them.
Oh yeah, that sounds good to me. Yeah, great.
Yeah, would you like to answer them now?
I can answer like 1 or 2, but if you don't have time, then I can type my answer in chat.
Oh, that also works. Okay. Yeah. So if you prefer to type the answer into the chat, or maybe have more discussions in the end.
Yeah, that sounds good to me. Yeah, thank you.
Sounds good. Thank you. Now we'll move to the next speaker, Dr. Xin Bing. Yeah, please feel free to start now.
Okay, now is it working for my microphone?
Yeah, it works well.
Okay, thanks. Thanks for the introduction, and it's my great pleasure of receiving this award. And I'm also very happy to be able to be here to share my research with you. So my talk is about inferencing latent factor regression with clusterable features, and this is a joint work with my lovely advisor, Flori and Martin. So even though the picture of Flori seems not that lovely, but she's a very lovely person. So the overview of my talk consists of 4 parts, and I'll start with a motivating application and also some backgrounds of the model. And then I'll start officially with the model formulation, and then followed up with some identifiability issue and the estimation procedure for the parameter of our interest. And then I'll conclude with the final inferential results of the model. Okay, so the whole project is motivated by a study on vaccine-induced humoral immune response, and the experiment was conducted by the bioengineering department at MIT. So what is in this experiment? So in this experiment, there are 60 monkeys that the researcher collected. And after being vaccinated, researchers measured their different antibody functional and biophysical properties. So there are 191 of them. And then the monkeys were unfortunately injected by the SIV virus. So the SIV virus is really the analog of HIV for monkey. And then in the end, different levels of protection of vaccine-induced protections were recorded for each monkey. So the final goal of this study is to determine and select those antibody-centric signatures of vaccine-induced protection against SIV. So just to be clear, that these antibody-centric signatures are something that people cannot measure directly. So you can think as these are summarized information of all those antibody functional and biophysical properties that people can measure. So basically, schematically in this experiment, what we have is the response for each monkey, which is a vaccine-induced index. And also people can measure different antibody properties from the monkey. However, what people really want to infer and determine are those unmeasured antibody-centric signatures. And these are kind of summarized information of those two detailed measurements. And these are this type of problem like we often encounter in practice. And throughout this talk, I will use Y to denote the response and X to denote the measurable features. And because of those factors that we cannot measure, I'll use the latent letter Z to denote it as the latent factors. So there are two goals in this project. The first one is to really determine what are those latent antibody-centric signatures, to determine this from those antibody measurements X. And then the second goal is really to select which of these latent factors are important for predicting the response Y. Okay, so these are two steps, and I'll briefly go through the first step because the first step can be used, can use some of those existing technique, and then my main focus of this talk will be on the second step, which is to provide a valid inferential tool for making inference on those selected latent factors. Okay, so to briefly go through the first step, we propose to really cluster those observable features via their association with the latent factors, and mainly because we know that antibody-centric signatures, even though they are not measurable, but they are functions of those measurable antibody properties. And therefore, we propose to group those antibody measurements into different clusters to determine those unmeasured antibody signatures. So there are two difficulties here we should have in mind. So first, we do not know how many antibody signatures or how many latent factors we have in mind beforehand. And this number of latent factors needs to be selected. And the second one is that because one antibody measurement can belong to multiple can be associated with multiple latent factors, or they can be generated from multiple antibody signatures, and therefore we should expect that the cluster structures are overlapping. So these are two kind of extra difficulty of this problem. And to solve this problem, like people can use a popular model is to use the latent factor models to model the relationship between the observable feature and the latent factor. So for instance, in this linear latent factor models, where the X is the really observable random vector and A is a P by K deterministic assignment matrix, you can think this basically represents the assignment of each observable feature to different clusters, where the clusters are being viewed as the latent factors. And Z here is a K-dimensional random latent factor, where we assume that K is unknown, but has to be typically is much smaller than P, which is the original number of features. And E here is some additive noise with uncorrelated interest. So now, how to use this model to cluster those observable random feature? We can use the following example served as an illustrating example. So in this example, we have 4 features, measurable, and have 2 unmeasurable latent factors. So if we know this assignment matrix A beforehand, then we can easily group the axis via the support of A. For instance, because we have 2 latent factors, one can think like this has 2 groups. And for the first group, we basically look through the first column of A and to look at which of those X are associated with this C1. And of course, obviously in this example, group 1 contains X1 and X3. And similarly, group 2 contains X2, X3, and X4, just by looking at the support of the second column of A. And however, and this is the way like we would like to use this latent factor model to cluster the observable feature. However, there are some intrinsic difficulty here, simply because either A or Z can, neither A nor Z can be observed directly, and therefore one have the freedom to insert any invertible matrices between them to construct a new matrix AQ, which has a different support than the original A. And therefore we are suffering some identifiability issue here. And the first goal is really we need to impose additional conditions such that we can have a unique A. Okay. So then in this like in this project, we will deploy the following identifiability condition, which is established in Bing et al. This paper. And this identifiability condition contains 3 parts. The first part is to assume the existence of canonical rows, which assume that the matrix A contains 2 K by K identity matrices. However, their positions are allowed to be unknown. And the second condition is about the scaling condition, which assume that each row of A has L1 norm no greater than 1, so that we can really interpret the matrix A as a assignment matrix. And the third condition is some kind of incoherence condition among the latent factors. It assumes that sigma Z, which is a covariance matrix of the latent factors, is strictly positive. And the second incoherence condition simply implies ZA is not equal to ZB in absolute value, almost surely. And I have some remark to make here for this set of identifiability conditions. So first, the first condition can be greatly relaxed in some recent work, but here the first condition is because of it's a common condition. It also termed as some kind of arrow Z variable parameterization in factor model literature to make the latent factors interpretable. And therefore, I will continue to use this set of conditions throughout the talk. And also in our example, like this condition A1 is expected to be hold, basically because for each of those latent signatures, we know that there are many of those antibody measurements that are only associated with this with one latent signature. So before moving on, I want to bring in another important notion, which is called the pure variables. And the pure variables are basically the features that correspond to the canonical rows of A. So take the following example. Suppose we have 6 features, and because of the existence of parallel rows, and we can name the pure variables in this example are x1 up to x4. And depending on which latent factor they are associated with, we can further partition these pure variables into 2 groups based on the latent factor Z1 and the latent factor Z2. And in general, when we have K latent factors or K groups, the pure variables can be further partitioned into K parts. And the one thing I want to mention here is that you might notice the assignment matrix A is allowed to have some negative entry. So the sign of A has really practical meaning, and our model allows this flexibility, because if you think X1 is some antibody measure and Z1 is some signature, if X1 is positively associated with this signature, it means that measurement activates this signature, otherwise it inhibits. So the sign of A really has some practical meaning in our context. Okay, so having this in mind, it has been proved in the previous work that under this latent linear model and all those identifiability conditions, the number of latent factors K and the set of pure variables I, as well as its partition, and also the assignment matrix A can all be uniquely identified from the second moment of X. Of course, like one can only identify the partition up to a group permutation. This is a well-known intrinsic difficulty of this problem. And I have a couple of remarks to be made here. All those identifiability results can be easily extended to estimation. By this, I mean the number of factors K, the set of pure variables I, and also its partition can be consistently estimated. And the algorithm for doing this is optimization free and has computational complexity order of p square. And the assignment matrix A can also be estimated with the optimal statistical convergence rates. So these are all proved results from the previous paper, and armed with all this result, we can apply to our data set to really form the clusters of those antibody measurements, and we obtain 10 clusters in total. And we can, this circles represents how we group those antibody measurements. And then we move to then we're ready to move to the second step, really to select which of those 10 antibody signatures are important or significant for predicting why. And before doing that, we have one thing to make sure. If we want to make inference on those latent factors, we'd better know what these factors mean, right? To know their meaning, that's important because that's what we are making inference on. And this is another advantage of the existence of pure variables, which are the canonical rows of X in A. The disadvantage is that the pure variables really render the latent factors interpretable, because the existence of pure variables saying that for each latent factor, you know some of the variable features that are only associated with this latent factor. So you can easily name these latent factors by those pure variables. For instance, in this data application, we can easily name the cluster 1 as the FC factor polyfunctionality and the cluster 2 as the antibody titer driven effects. And therefore we really understand the meaning of these different latent factors, and we are ready to make inference on them. So to make inference on the Z, or to select the Z, we propose another layer of the model, which is a linear model between Y and Z. And these two equations are known as the factor regression model, and we call this framework essential regression if the additional identifiability conditions hold on the matrix A. And our goals are twofold. The first goal is to identify and estimate the linear coefficient beta, which links the latent factor Z and Y. And the second goal is really to make inference on beta. So the factor regression model is well known for prediction mainly, just because of the ambiguity of the meaning of latent factors. However, there are many particular factor regression models where the Z can be interpreted or can be determined, and for instance, in this essential regression model. However, the inference on beta or estimation on beta, I mean, the literature on this part is relatively less studied. So these are some quick review of the existing literature. So if the number of latent factors K and the number of pure variables are not known, to the best of our knowledge, there is no work on this for making inference on beta. And when K and I are all known, Anderson and Rubin, as early as 1956, they have analyzed the MLD estimator. However, according to their paper, the asymptotic variance of the MLD estimator is too complicated to derive even. And if the number of features P is allowed to grow, by ND in 2012, they analyzed a MLD type estimator where they successfully derived the closed form asymptotic variance of the beta. Lowever, their work is really imposing some strong signal conditions on the low rank part. And also the EM algorithm they analyzes only converges to a stationary point. And moreover, there is no consistent estimator known for the asymptotic variance. So summarizing, so far, we do not have a valid inferential tool for making inference on the coefficient of beta, even in this ideal case, where K and I are all known and K is fixed, P either fixed or growing. So our hope is really to fill in all those gaps in these different regimes in this project. So to start with, we need to first make sure that the linear coefficient beta is indeed identifiable. And this result showing that this is indeed the case, and it can be identified from the first two moments of X and Y. So just to illustrate how we identify beta, the key here is really to first identify the set of pure variables I. And after knowing this I, we can recover this matrix, which is a P by K matrix. It's a product between A and the covariance of latent factors Z. And from here, a key observation is that the following equation holds. And therefore, beta can really be solved from this equation. And motivated by this key observation, this leads us to a very natural estimation procedure, which is to use the plugin estimator by replacing all those I by I hat, theta constructed from sigma by sigma hat, and also replace the covariance between X and Y by their sample counterpart. So this leads to the final estimator of the beta, which is a very simple estimator. And this plus means the pseudo inverse whenever the sigma hat transpose sigma hat is not invertible. So for such an easy estimator, does it have a kind of desired property statistical property? So we start with its statistical convergence rate. So under some mild regularity conditions, for instance, some sub-Gaussian entity tails of the random variables and random vectors, we are able to establish the following result. The L2 norm of beta hat minus beta exhibits the following convergence rate under the condition that K is a smaller order of n. And for this type of convergence rate, the M here is the smallest number of pure variables among all the group. And the beta 2 norm is really the 2 norm of the coefficient beta. And to interpret this rate, suppose that suppose we can observe Z, and then estimating beta is a classical problem because the least square estimator will give us the square root K over N rate for estimating a K-dimensional parameter from n IID samples. However, because Z is not observed, this type of convergence rate is non-standard, and the additional price one needs to pay, it depends on this beta 2 norm over square root n. So is this price really necessary? And we try to answer this question by establishing the following minimax lower bound. So the parameter space we are considering is the following, where the covariance matrix of Z are well behaved, and the 2 norm of beta is controlled by the radius R, and also the matrix A satisfies all the previously mentioned identifiability conditions, and with M equal to the smallest number of pure variables among all the group. And we can see that the minimax lower bound tells us the semi-exact rate is exactly the minimax, is exactly the minimax rate. And this suggests 2 points. So first, our estimator is really minimax optimal. And then the second point is that this additional price is really the intrinsic difficulty of this problem. And this is the non-standard rate. For instance, one might think that the 2 norm of beta is typically represents the signal strength in regression, right? And I would think that the larger beta is, or the larger R is, the easier this problem becomes, so that we can obtain a faster rate. However, we're observing a kind of a converse phenomenon, that is, the larger R is, actually the problem gets harder. And this is because we are not observing Z, so we cannot really interpret this beta 2 norm as the signal strength as usual. And this explains why this type of rate is non-standard. And our minimax lower bound also generalized the lower bounds for errors in variable model, where basically all the variables are pure variables. So moving apart from the convergence rate, we're ready to talk about the inferential part, which is our main interest. And we are able to establish the following coordinate-wise asymptotic normality of beta hat minus beta. So with probability tending to 1 for each coordinate, we have the following asymptotic statement, where beta hat k minus beta k scaled appropriately converges to a standard normal distribution. So here I want to emphasize that the asymptotic variance we can derive its exact expression, even though it's quite complicated. And also this asymptotic variance can be consistently estimated just by some simple plugin estimator. So combining these two facts, Slutsky theorem tells us that we have a valid inferential tool for constructing confidence intervals for each coordinate of beta, or to conduct hypothesis testing. Before moving on, I want to briefly mention the outline, some outline of the proof, because the proof is highly technical, but it mainly consists of 4 parts. So the first part is to recognize this decomposition for each coordinate of beta hat k minus for each coordinate of beta hat minus beta. The first term of the decomposition is a sum of independent terms psi ik, and the second term is some remainder term. And the first remainder term quantifies the error of estimating this p by k matrix, the product of those a and sigma z, and the second term quantifies the error due to the estimation of the pure variables. And the second step is to study those independent terms, Xi Ik, and some complicated. I mean, it's to show that it's mean zero is not quite complicated, but to derive its second moment, the analysis is pretty difficult, and we are able to show that second moment is equal to Vk, which is exactly the asymptotic variance term. And the third term is really to apply the Lyapunov-Central limit theorem to the sum of those independent terms. And because of the triangular array structures, since that Xi Ik contains the terms involved with K, P, sigma Z, all of which are allowed to grow with N. And therefore, this term is exhibiting some triangular array structure. One need to apply the Lyapunov-Central limit theorem by checking the third moment of each of this term. And to bound the third moment, we need to use the Rosenthal inequality to bound the sum of certain sub-exponential random variable. The final step is to show that all those remainder terms are ignorable comparing to the asymptotic variance. And this term is also quite complicated due to some technical issue. For instance, you need to establish the existence of this matrices, and also you need to provide some union bounds over all those random terms. And this concludes all the proof.
4 minutes.
Yeah, 1 minute.
Oh, 4 minutes.
Okay, 4 minutes. Okay, I should be able to finish that. So far we have derived a valid inferential tool which can be used for downstream analysis, such as FDR control. And our analysis unifies all the scenarios for both fixed P, fixed K and P, and growing K and P. And also we are able to provide a computationally tractable estimator, as well as its consistent estimation of the asymptotic variance term. So by applying this technique onto the data set of the monkeys, where we conclude that among those 10 latent factors, only 2 of them are significant for predicting Y, and they correspond to the FC factor, polyfunctionality, and antibody titer-driven effects. So this perfectly is perfectly aligned with the biological expectation, and our collaborator seems very happy with this result. Okay, so before ending the talk, I want to mention another interpretation of the essential regression. It can be treated as a regression on latent cluster centers. So recall that we have the following linear model where the assignment matrix, the matrix A is assignment matrix. So intuitively, this X bar denoted as the following can be treated as the weighted cluster centers. However, a important remark is that the linear coefficient beta is not equal to the following expression, which means we regress Y onto this weighted cluster centers. So this is not equal in general. In fact, this can be easily corrected by regressing Y onto the best linear predictor of Z from X bar. So this is a key observation, and this also suggests, in practice, if the model holds, then when to estimate beta, when this kind of naive or most common way of estimating beta will not give you the correct coefficient. However, this can be corrected by the best linear predictor. And also a quick remark that our estimator is also the order least square estimator by regressing Y onto the estimates of this best linear predictor. Okay, a quick summary. We have studied the following latent factor regression model. We talked about the identifiability of beta, and we proposed a computational efficient estimator of beta, and studied its adaptivity and the minimax optimality. And we also provide some valid inferential tool over beta. And by looking at this model, you might recognize that the beta can be treated as one particular row of A if you put these 2 models together. And so our derived inferential tool is also suitable for if you are interested in making inference on certain row of A. I think this concludes all my talk. Thanks for your attention.
Thank you. Thank you for the great talk. Now we have quite some time for questions. Let's see whether there are any questions from the audience. Okay, maybe may I ask a question?
Sure. Of
So
course.
they have this very nice idea of finding pure variables. And in practical algorithm, it's chosen subject to some threshold. I'm just wondering how to pick the threshold in practice if we for a given, for example, data set.
That's a very, very important aspect in terms of practical implementation of the algorithm. So we have two versions for finding those pure variables, and this is the structure based on the structure presented here. That algorithm, we have a data-driven way of selecting that only for sub-Gaussian distributions, and that kind of data-driven way also need a cross-validation tune. You basically have the theoretical order, and to select those initial constant, you start with a grid, and for each of those, you use a criterion to find the best one. And however, in the most recent version, like we have a better way of doing this. So that way is it's a different algorithm for selecting the pure variables, but it will gives you a kind of it has the rationale as the cross-validation used in Lasso. So basically you start from a monotone grid, and for each of those grid, you can prove that your clusters are hierarchical. So you have a more smooth structure there, and from there, I think practically, if you have some prior information in practice, you know where to end. Otherwise, it automatically gives you some kind of best thresholding, which for certain it will return the threshold which minimize some kind of loss function via some cross-validation procedure. I would like the second one, because for this first algorithm, it cannot guarantee that the group structures are hierarchical. So it means that the group structures are not smooth in this sense. So it's a little bit hard to decide where you stop. But if you have a kind of hierarchical group structure, it is a bit more easier for the practitioners to decide where to stop there.
I see.
But in general, that's a very important issue, and I'm not sure if I have a better answer for this so far.
So I think this is already a satisfactory answer. Yeah, thanks. And let's see whether we have other questions from the audience. Okay, there still seems no other questions, and then I want to thank all three speakers again. And then we will have some time for floor discussion. Maybe I will stop the recording now, and then everyone is free to ask questions and participate in the discussions. Okay, so yeah, we'll stop the recording.